How about now? Can you hear me now? Oh, okay, perfect. Okay, so just hello everyone. Just change my headphones. And okay. Okay, 26 of you. Okay, we'll start in a bit. So yes, most of you. So we've checked the work. There were about just under. Still can't hear. Can you hear me now? I can. Yes. Okay. So there were just under 200 of you sent in the work, and we are accepting about. Well, we don't have the final numbers of accepted people, but basically it's about 100. So there's 21 papers remain unmarked. So very sorry about this. Sorry to keep you waiting, but hopefully you all got your email, the email today, which says whether you're in, not in, or undecided. Okay, so let's start. So kinematics. Kinematics is a very interesting part of mechanics. So basically, it's a part of physics and a part of maths at the same time. So I'll share my screen as usual, and I will share the link with you as well, so you can just find the chat. Okay. Right, so I prepared some problems for you today. Some of them are very, very similar to the ones in the assignment. Some of them not so much, but hopefully it will all make sense to you. Okay, so the first problem. So you have two roads intersecting at right angles, and when car 1 is at O, so when car 1 is at the point of the intersection, the car 2 is a distance L0 away. So what do we do here? Find the minimal distance between the cars. So we can draw the diagram a few moments after. So let's say t seconds have passed. So car 1 has moved, and car 1 has moved, let's say, a distance y. And car 2 has also moved, and now it's here. So it used to be here, now it's here. And let's say the distance to the crossroads is x. We need to find the minimum value of this length, and we'll call this d. So you could probably see the Pythagoras theorem here. The only thing is that we need to figure out what x and y is. Well, y is very simple. Y is the speed of the car, v1, multiplied by the time. And x is the initial distance, L0, minus v2t. And from here, we can write down that the distance between the cars, well, the square of the distance, let's make it simpler. The square of the distance between the cars apologies for the handwriting, is V1 t squared plus L0 minus V2t squared. Now, if you had numbers for the speeds of the cars, that would be a very simple question. But you have to stretch yourself sometimes in working with algebraic expressions. This makes physics way more difficult and way more interesting at the same time. Because you kind of get the answer is a formula which allows you to sub in any values. So what we're going to do is first, we're going to expand. So V1 squared t squared plus L0 squared minus 2 times L0 V2t plus V2 squared t squared. Now combining the like terms, these are like terms, I get V1 plus V2 t squared minus 2 L0 V2t plus V1 squared t squared. And this is obviously equal to d squared. So yes, d squared. Right, so, well, oh no, sorry. What did I made a mistake. L0 squared. L0 squared, of course. So V1 plus V2t to L0 V2t plus L0 squared. And this is a quadratic. This is a quadratic, and what we need to find the minimum value of a quadratic. V1 plus, that is correct, thank you. Just a second. No, it's going to be apologies, it's going to be V1 squared plus V2 squared. Oh, that makes some changes. Just give me a moment. And squared, squared, squared. Okay, not dramatic. Squared, squared. All right, yes, that makes more sense. Okay, so it's a quadratic, and to find, yes, complete the square. You could use calculus, and in fact, in this case, calculus is much simpler. It's much simpler. But the problem we had in the test is not it doesn't asks you not to use calculus. So to find the minimum value of a quadratic, we will complete the square. So we'll take V1 squared plus V2 squared out of the brackets, and we're left with t squared minus 2 multiplied by L0 V2 divided by V1 squared plus V2 squared times t plus L0 squared divided by V1 squared plus V2 squared. Okay, we can kind of forget about this v1 plus v2 squared and focus on this bit. And but I'll carry on doing it as it is, even though it might be a tiny bit more confusing. So completing the square here, so we write v1 squared plus v2 squared. So t squared minus 2 times this term, 2 times L0 v2, and v1 squared plus v2 squared, t plus, now we need this term squared, so it's going to be L0 squared v2 squared, right, divided by v1 squared plus v2 squared, and minus the same thing, so minus L0 squared v2 squared divided by v1 squared plus v2 squared plus L0 squared by v1 squared plus v2 squared. Okay, close bracket. And we're almost there. So from here, I can write that d squared, is this thing that we're looking for, is v1 squared plus v2 squared, open bracket, t minus L0 v2 divided by v1 squared plus v2 squared, close bracket. And now very accurately expanding the rest. So what did I forget? I forgot the square here. And I forgot the square here. Okay. v1, and then that's a squared term. Okay, I'm not in a hurry to expand. And then we have actually I will expand. I will expand right away. So when I expand this, I get, all right, L0 squared v2 squared v1 squared plus v2 squared. Now there's no square down here, and plus L0 squared. Now, the beautiful thing about this quadratic is the quadratic is a minimum when this term is 0. Yes, the quadratic is a minimum. So it's a parabola, and you need to find the minimum point. And the minimum point is when this is 0, because it is a square term. It cannot be negative. So it is greater or equal to 0. So the lowest value is 0. So this has to be equal to 0 when d is minimum. Therefore, if this term is 0, this means that this term is the minimum distance. So the minimum distance, d minimum, is equal to this. So square root of L0. I won't fully simplify it, minus L. Actually, why not? Yeah, I can simplify it. So you know what? I will write d minimum squared, and I'll simplify it right away. So I'll find the common denominator. So it's going to be L0 squared V1 squared plus L0 squared V2 squared minus L0 squared V2 squared. And these cancel out. And we're left with a V1 squared plus V2 squared. So D minimum is equal to L0 V1 divided by square root of V1 squared plus V2 squared. So when you're doing physics on a high level, your answers will always look something like that. Your answers will always be in terms of the variables, in terms of the initial parameters. And then if you have the parameters, you can simply just plug it into the formula, and you get the answer. The thing is that it will work for any similar problem with any V's and any L's. And that's the beautiful thing about it. Complete square, differentiate, yes, differentiate to find minimum. Okay, so this problem is way harder than the one in the assignment, because in the assignment you're given values, you're given the speeds. Let's see. I think it is. You won't be able to get a mark scheme, unfortunately, but you can cooperate with other people, successful or unsuccessful in the program, just to discuss the problems, and you can also attend webinars. Okay. The passenger is late for a train and runs along the platform at 3 meters per second. Now, this is an old problem when trains were a bit different. And even in my time when I was growing up, if the train leaves, that didn't necessarily mean you missed it. If you can run fast enough, you can still get onto the train. Happened to be a couple of times, but now it's obviously trains are slightly different. But I decided to keep this problem, even though it doesn't make much sense now, because once the doors are closed, you can't board the train. But it used to be different. Trains had open doors, and you just jump in if you can. So a passenger is late for a train and runs towards along the platform at 3 meters per second. The distance between the passenger and the last door of the train is 12.5 meters. Yes, you would know your marks. It just takes time for me to send them. Okay, so I have your marked assignments. It will just take time. A passenger is late for a train. So let's model this. So this is a much simpler question. So you have a passenger, and he's running along the platform at 3 meters per second. 3 meters per second, and there's a train, which is 12.5 meters away. 12.5 meters away, and it's starting to accelerate at 3 meters per second. Now you can, at 0.2, acceleration of 0.2 meters per second squared. Of course, you can solve this by Suvat. That's Suvat. But I want to demonstrate to you how you do it using the equation of motion. because the topic of the assignment is equations of motion. So for the passenger, you can write R is equal to R0 plus VT, V0t plus acceleration, but there's no acceleration. So this is the equation of uniform motion. Now, because we're doing it in the x-axis, we're projecting it on the x. So we're only interested in the x component. So we can write xt. So this is rt, is the function of time, is the initial position. We can assume that the passenger starts at position 0 plus velocity 3 times time. So this is the equation of motion of the passenger, x1. For the train starts at initial position 12.5. So for the train, the equation is different because this is uniformly accelerated motion. So R0 plus V0t plus 1/2 AT squared. So we are projecting it on the x-axis. So this is a projection. Can you use calculus for this? Theoretically, you can, but I don't see why would you? It's much easier to do without calculus. So x2, the coordinate of the train at any moment in time, is the initial position of the train, which is 12.5, plus the initial velocity of the train, which is 0, times t, plus 1/2 times the acceleration, 0.2, multiplied by t squared. And we get two equations. x1, this is the position of the passenger at any given moment in time. And this is the position of the train at any given moment in time. This is the aim of mechanics. The aim of mechanics is to know where a certain object is at any given moment in time. Lagrangian mechanics. No, not really. We won't do pendulums. We won't do the equation of motion of a pendulum. Okay. So when they meet, that means x1 is equal to x2. So 3t is equal to 12.5 plus 0.1 t squared. Now, you can obviously do this with suvat. Yeah, the suvat that you are very familiar, you're all familiar with. But this is done through the equations of motion, and this gives you more flexibility. And now it's a quadratic equation. Now you solve the quadratic. Now you all know how to solve quadratics. I won't show you. Or if you don't know how to solve quadratics, it will. This will be a secret. So 5 seconds, and t2 is equal to 25 seconds. This is and this. Yeah, so we need to choose the correct answer. But how do you know which one is correct? Well, if you draw the graphs of motion of both, you will see that this is the graph of motion of the passenger. X and t. So x equals 3t. This is the equation of motion of the passenger. This is the graph of motion of the passenger. And if you draw for the train, well, the train goes like this. It starts from this point, and then it is a parabola. So actually, the train and the passenger meet twice. The train and the passenger meet twice. First time is when t is 5. T is 5. And the second when t is 25. Now, if you're a passenger running for the train, obviously, well, basically you have 2 attempts to board the train, but the second time the train is moving much faster. It will be moving twice as fast as you, so it would definitely would be unsafe. But if you plug in 5, you can see that the plug in 5, so where will they meet? So this is the answer. This is the first time the passenger kind of runs past the train, and then the train catches up again. So obviously the second answer doesn't make any sense. So if t is 5, if you plug that in, x1 is equal to 15 meters. So the train would have only moved 2.5 meters. So yeah, it is sometimes possible. Don't try this at home. Don't try jumping a moving train. These essentially to derive equations of motion. Okay, I had this question already. Okay, I hope that makes sense. The interesting physics happens here when you are deciphering this. You're deciphering this and trying to make sense of it. Oh, well, how do I know? Oh, we can write a similar equation for the velocity. We know that the velocity, one of the Suvat equations, is that velocity is the initial velocity plus acceleration multiplied by time. So velocity at 5, when at 5 seconds, the train is moving at, so that's 0 plus acceleration, which is 0.2 times 5. 0.2 times 5. So that is actually 0.2 times 5 is 1 meter per second. And velocity at 25 is going to be 0 plus 0.2 times 25. Oh, 12.5. Yeah, sorry, that was wrong. That was my educated guess, and it completely went wrong. I did not verify it. So the second time, the train is moving at 12.5 meters per second past you. So it's definitely unsafe to jump to try to board a train moving at that speed. So, but 1 meter per second is, well, doable. Is it not 5? Sorry. 5 meters per second. Yes, thank you. Thank you. All right. Okay, so 5 meters per second. 5 meters per second, that is still fast. Okay. Now, this is a pad question. The graph shows the velocity of a rocket as a function of time. No, the initial velocity of the train is 0.24. Yes, 0.2 times 25 is 5. Problem 3. This is a pad question from 2006. So this is a graph of the velocity of a rocket as a function of time. What has happened at point X? Yeah, can somebody guess what happened at X? Yeah, engines come off, or it's out of fuel. Yeah, the rocket turned off effectively. Yes. The rocket has switched off. So we have going X, and then suddenly the velocity stops increasing. That means that the engine's off. Engine's off. When is the acceleration of the rocket a maximum? Well, the acceleration is the gradient of the graph. So the gradient is maximum, well, around this point. The acceleration is maximum right before it switches off, somewhere like 55 seconds. 55 seconds roughly. So between 50 and 55 seconds. Now, a reason. Why is it maximum at this point? Why is it maximum? Can somebody try to understand? Exactly, yeah, very good. Because F equals ma, and acceleration is F divided by m. So if you have the same force, but as the fuel burns out, the mass decreases. As the rocket runs low on fuel, mass decreases. And for a given force, you have more acceleration. Yeah, so a heavier rocket will have less acceleration, and a lighter rocket has more acceleration because A equals F over m. The smaller the mass, smaller mass. I'll just write it down. Describe the subsequent motion of the rocket. Now, this is a very common mistake, and it catches out a lot of people. And this is a common question on the Oxbridge interviews. People say that it is in free fall, falling down. Well, it is in free fall, but actually it's moving up. The rocket is in free fall, and but it's still going upwards. So it is going upwards, and decelerating. Upwards, decelerating. And when the line reaches the x-axis, or the t-axis in this case, the t-axis, that's when it reaches the maximum height. So this is out of fuel, and this is a maximum height, max height. And if we continue the graph, then somewhere here it will reach the ground. So it touches the ground and very quickly decelerates. Well, assuming it crashes into the ground. So this is crash. And the interesting thing, describe how in principle would you determine from the graph the maximum height reached by the rocket? Well, the maximum height is equal to the area under this part of the graph. So area is maximum height. To determine the max height, we just look at the area. Exactly. And this area has to be exactly equal to this area, because the distance traveled upwards has to be equal to the distance traveled downwards. So this area, these areas would be the same. Area 1 is equal to area 2. Area 2. Okay, so lots of stuff going on in here. Now, when you draw this, the deceleration of the rocket is finite. If you draw a vertical line, that means infinite acceleration. But here, acceleration is finite. It's very big, but it's finite. Okay. All right. Small mass. Hope that's making sense. Now, problem 4, you need to find the acceleration from the graph. Well, we know that the acceleration is the gradient, is the slope. So acceleration is the gradient. So it's minus 15/6. And that is minus 2.5 meters per second squared. Okay, that's the acceleration. Find the equation of the velocity. Well, we know that with uniformly accelerated motion, we need to find the velocity versus time. But it's actually just the equation of this straight line. So we know the slope, which is minus 2.5 t, and the y-intercept, which is 15, plus 15. Now, equation of the position of the object. So the equation of motion, very good. Yes, integrate. But you can also use the equation that we already have. We know that x of t is equal to x0 plus v0t plus a half at squared, which is one of the Suvat equations, which is a modified Suvat equation, because if you write s is equal to, s is equal to v0t plus a half at squared. Well, s is x minus x0. That's the difference between the current position of the object and the final position of the object. So v0t plus 1/2 at squared, and then you rearrange that to make x is equal to x0 plus v0t plus 1/2 at squared. That's where this formula comes from, but also it's the component of this equation. Okay, I won't write out this equation. Okay, so we have this equation. So now we just need to substitute what we already know. We know that the initial position, we don't know the initial position, so we'll leave it as x0. That's the initial position, plus the final the initial velocity is 15t, and plus a half at squared. So a is minus 2.5, so it's going to be minus 1.25 t squared. This is the equation of motion. This is the velocity, and this is this. And yes, Jakub said integrate. Of course we can. Of course we can. We can do it in two different ways. We can do it like this. So we write down v is equal to minus 2.5 t plus 15. Yeah, absolutely. And we know that velocity is the derivative of x. So dx dt. If you haven't done integration yet, don't worry. Don't worry. This is just a heads up for you of some interesting stuff happening. And if you multiply this by dt, you multiply both sides by dt, you get dx equals minus 2.5 t plus 15 dx. And then you integrate. So this means just literally drawing these curves in front. And if you integrate, the integral of dx is x. The integral of this is minus 2.5 t squared over 2 plus 15t plus c, where c is an unknown value. dt on RHS. Of course, sorry. dt. Thank you. All right. Focus has shifted. We know that when t is 0, the x is x0, it's the initial position. So we plug in t equals 0. T is equal to 0, x is equal to, so x0 is equal to 0 plus c. So x0 is c, so c is x0. So the equation, this equation becomes x is equal to minus 1.25 t squared plus 15t plus x0, which is exactly what we have, here. Here. There's a different way of doing integration. And I think that I like this method even more. Using proper integrals. Now we know that initially x is x0, so x changes from x0 to x. And we know that t changes from 0. The initial value of t is 0. The final value of t is t. So x changes from x0 to x, and t changes from 0 to t squared. So it's minus 2.5 t plus 15 dt, of course. And if you integrate that, this is going to be x between limits x0 and x, and equal to minus 1.25 t squared plus 15t between limits of 0 and t. So x minus x0 equals minus 1.25 t squared plus 15t plus 0 minus 0. So it's the same equation. X is equal to x0 plus 15t minus 1.25 t squared. It is nicer. It's less messy, because what I found when I was studying and now. Like this is a mess when you're trying to figure out C. With limits, it's just, yeah, it's very elegant. So we'll do lots of this later on when we're going to do radioactive decay. So don't worry if you don't know integrals yet, or you don't understand integrals. Yeah, knowing integrals and understanding them sometimes takes a long time. Integration is, I guess, the most important skill for a mathematician or a physicist. So you can get away with some stuff, but not integration. Okay, problem 5. Real analysis, which is discretion. Okay, well, integration from first principles is, yeah, definitely good for it. You introduce the sums and stuff like that. So Aston, this is a very unusual question. So a question similar to that is in the assignment, but this is a little bit harder. So I decided to stretch you a little bit here. So you have an inclined slope. You need to understand one very important principle when you are dealing with inclined slopes. One very important method. I think principle. So you have a stone which is launched at an angle. So it's launched at an angle, and there is the angle here. So I'll call this angle theta, and I'll call this angle, actually, I'll call this angle omega. So as you understand, theta is 30 degrees, and omega is 60 because it is 30 degrees here, another 30 here, so a total of 60 here. A stone is launched at an angle 30 degrees from the top of a 30-degree inclined slope with an initial velocity of 20. But I'm gonna make it u. I'm showing you the physicist approach to doing stuff, like the kind of approach you would be expected to use at a top university. Because you're not always given the values. I mean, these are kind of values which give you a beautiful answer, but they don't necessarily show you how to solve it algebraically. Okay, so we have this. Now, the most critical point here is that you need to draw a frame of reference. We don't normally talk about frames of reference at school, and that's a pity. But you need to understand that we send the x-axis along the slope and the y-axis perpendicular to the slope. It's not horizontally and vertically, but along the slope and perpendicular to the slope. X. And now you can write down the equation of motion of the projectiles of the stone. So basically what you do is you don't physically have to do it, but you can do it in your head. You kind of turn this. You turn this sideways. You turn the picture sideways, and you have the x-axis going along the slope. the y-axis going up. And we're going to work with this. This is the y-axis. This is the x-axis. And the stone will travel like this and land somewhere here. We call this distance L. And now you kind of need to understand that the gravity in this example is directed like this. So the acceleration, or well, G in this case. And now resolve. Yes, resolve along the slope and perpendicular to the slope. So you can write down that R is equal to R0 plus V0t plus 1/2 AT squared. And so vertically, R is x and y, x of t and y of t is equal to the initial position, which is 0, 0. R is the radius vector. The radius vector is it's the vector with the coordinates. So let's say the object is at point x, y. R is the vector drawn from the origin to that point. This is vector R. And the coordinate of this vector, this is why I started, that's why the first assignment was vectors, so you can understand this. So vector R has coordinates x and y for any point. So it's called the radius vector or the position vector of a point. Okay, so this equation gives you the coordinates of the vector. So the vector R is the x and y coordinate of the object. 0, 0 is the initial coordinates of the object, plus velocity, which is u cos omega, so that's the horizontal component of the initial velocity. That's u cos omega, and this is u sine omega, u sine omega multiplied by t plus 1/2 multiplied by the acceleration. But the acceleration also has to be split into components. So this angle is theta. So this is g sine theta. And this is minus g cos theta. So this is going to be g sine theta and minus g cos theta. 0 in x. No, it's not wrong. Wrong. What do you mean? Sorry, 0 in x. Okay. 0. Okay, t squared. Yeah, I've made so many mistakes today, it's embarrassing. Now we write two separate equations for x and for y. X of t is equal to u cos omega t plus 1/2 g sine theta t squared. And y of t is u sine omega t minus 1/2 g cos theta t squared. Now, well, we know that at the point where it lands, y is 0 at this point. So we solve this for 0. Because it can be very confusing. The concepts that are behind this are can be very difficult for people with non-mathematical type of thinking. And yeah. So we know that y is 0 when it lands, as it lands is 0 when lands. And we solve it for t, so we substitute, we factorize, and so with u sine omega minus 1/2 g cos theta t equals 0. So one of the solutions is t is 0. Well, when t is 0, y is 0. Yes, always. I mean, that makes sense because we start from 0. So this is a solution, but it doesn't make sense for us. So we need the other one. And the other one is when this bracket is equal to 0. So it's a factorization product of two numbers equal to 0. So t is 2u sine omega divided by g cos theta. No, you can, of course, you can develop mathematical thinking through solving problems. But the thing is that at school, you're normally like, you're not always challenged at school to the extent that you need to be challenged in order to be able to tackle these questions. No, it doesn't work like that. It only works if the argument is the same. So sine omega divided by cos omega would be tan omega. But sine omega divided by cos theta is not a thing. But we know omega and we know cos, we know theta. So we we know omega, so it's going to be 2u multiplied by sine omega, and omega is 60, so sine 60 is square root of 3/2 divided by g cos theta. Well, cos theta is cos 30, so it's also square root of 3/2. So square root of 3/2 cancels out. And we know that u is 20 and g is 10. We just take 10 for this for now. So it's 2 times 20 divided by 10. So it's 4 seconds. So the time of flight is 4 seconds. And from here, we can find x. So the range is x of 4. So it's the distance, the horizontal distance after 4 seconds, the horizontal displacement after 4 seconds, which is u cos omega t plus 1/2 g sine theta t squared. So you plug in the values. So it's 20 cos omega, so that's cos 60, so it's 1/2. Then we have t, which is 4, plus 1/2 times 10 times sine 30, which is 1/2, and times t squared, which is 16. And after you do the arithmetic magic, so 10 times 4, it's 40. 1/2 times 10, 5. 5 times 1/2, 2.5. 2.5 times 16 is 40. 40. So the answer is 80 meters. So the stone will end up 80 meters down the slope. So it will travel 80 meters and land, yeah, 80 meters. Now, an interesting question would be at what speed it would land. And the easiest way to answer that question would be using energy. You can differentiate x. Nah. Oh yeah, by all means. By all means, you can write down the vector RT. Actually, that's a cool thing to do. So let's do it. So I'm going to write down the vector RT, and it's going to be u cos omega. So I'm going to plug in the values. Cos, so u cos. So I'm taking this from here, just for you to understand. I'm taking these values and plugging them here. So it's going to be x of t, y of t, and x of t is u, which is 20, then cos omega, so cos 60, so it's 1/2, and t plus 1/2 times 10 times sine 30, which is 1/2, t squared. And then y is u, which is 20, sine omega, so sine 60, so it's square root of 3/2, t, minus 1/2 times 10 times cosine theta, so it's cosine 30, so square root of 3/2, t squared. We simplify that. So 10t plus 2.5 t squared And here we get 10 root 3 t minus simplifying 2.5 root 3 t squared. And now the magic. Velocity is the derivative of r. Sorry, guys, those of you who haven't done differentiation yet, I'm sorry, but this it won't take long. I mean, if you don't know this, don't worry. Don't worry if you don't understand what's going on here. If you don't know how to differentiate, you will learn very quickly, and then you can get back to these notes and try to make sense of it. 3t minus 2.5 root 3t squared. And when you differentiate that, you get 10 plus 5t and 10 root 3 plus 5. Why is it minus 5 root 3t, and then we need to find the speed at 4 seconds. So after 4 seconds, the speed is 30. Well, 10 plus 5t, 10 plus 5 times 4, and 10 root 3 minus 5 root 3 times 4, which is 30, and minus 10 root 3. And the velocity is the speed. The speed is 30 squared plus 10 squared times 3, which is something. Which is something. Right. I'll just ignore that. So you have 30 squared plus 300, 20 root 3. So 20 root 3, so that's what, 34. 20 root 3. 20 root 3 is 34.6. 34.6 meters per second. So that's the speed of the stone when it hits the ground. So yeah, I mean, it is genuinely quite cool. So problem 6, a ball was sliding down. Sorry, I said rolling, sliding down. Sliding. This is a very important distinction. Sliding down the frictionless slope along AB. Find the time to reach B. And then radius is 2 meters, G is 10 meters per second squared. How does the time change if alpha changes? So basically, we're trying to figure out, would it roll faster to C, or will it roll faster to D? On one hand, it will roll faster down AC, but it has a longer way to go. Along AD, it has a shorter way to go, but it will roll down slower. So that's what we're going to try to establish. So let's say it's rolling, sliding down AB, sliding down AB. And we're going to use the same principle. We're going to, but because this is a one-dimensional motion, we'll just direct the x-axis along AB and put the origin at A. So this is the origin. This is the x-axis. And we have the G. So this is G, and this is alpha. So this is G. This is the component of G. This is the G cos alpha. G cos alpha. And then we just write down the equation of motion. So we know x is equal to x0 plus initial velocity v0t plus 1/2 at squared. Now, because I've pointed down, you can see that this component is along the x-axis. So it's along the x-axis. It's the same direction as the x-axis, and that is why it's going to be a plus. It's going to be a plus here. So x is equal to x0, which is 0. The initial velocity is 0. T plus 1/2. Acceleration along the x-axis is g cos alpha. G cos alpha t squared. So in other words, x is equal to 1/2 g cos alpha t squared. So that's the first thing that we need to establish. So this is the position of the ball at any point of time. We can, usually we say x of t. Now we need to establish how far it has to go in terms of the radius. And to do this, we're going to use the cosine rule. Using the cosine rule, which you should be familiar with. So first we need to find this angle. If this is alpha because these are the same. So this is the radius and this is the radius. And this angle is pi minus 2 alpha. Okay, pi minus 2 alpha. So using the cosine rule, we have AB squared is equal to radius squared plus radius squared minus 2 times radius times cosine of pi minus 2 alpha. Okay, so this simplifies to AB squared is equal to 2r squared minus 2r squared cosine. Now, on a side note, we know that cosine of pi Is it not 180 minus 2 alpha? Yeah, exactly. But pi is 180. Pi minus x, one of the formulas that you'd had in the maths assignment is that it's equal to minus cosine of x. That means that this can be replaced by minus cosine 2 alpha. Okay. So AB squared is equal to 2r squared, 2r squared, open bracket, 1 minus cosine 2 alpha. So we just factorize it. Now we remember that cosine 2 alpha is equal to 2 cos squared alpha, 2 cos squared minus 1. This is one of the formulas, minus cos x. Yes, minus cos x, and 2 cos squared alpha minus 1. So we plug that into here. AB squared equals 2r squared 1 minus 2 it's plus yes, thank you. Yeah, notice that. So it's going to be 1 plus 2 cos squared alpha minus 1. 1 cancels out, and we get AB squared. B squared is equal to 4r squared cos squared alpha. Okay. This is the distance traveled. So AB is equal to 2r cos alpha. 2r cos alpha. 2r cos alpha. And then we know that when it reaches B, when it is at B, it has traveled this far. This is the displacement. So we plug that into here. We plug that into here. And we get that from here, we get that 2r cos alpha. 2r cos alpha is equal to 1/2 g cos alpha t squared. Cos alpha cancels out. And we get t squared is equal to 4r divided by g. Yes, thank you. So t is equal to square root of 4r divided by g. Okay, we got this value, but what's the significance of that? Well, the significance of that is that no matter alpha, time is the same. Time does not depend on alpha. So if you had a hula hoop placed vertically and you had ramps all the way down, every ramp would take exactly the same time if there's no friction. So rolling down AD, rolling down AC, and rolling down AB sliding down AD, sliding down AC, and sliding down AB would take exactly the same time. And of course, you can just plug in the values now. So R is 4 times 2, 8, divided by 10, 8 10th, square root of 0.8, something. It is something like 0.9 or 0.9 seconds-ish. Not the most interesting. You see how these values, I haven't used them until the very end, because you're not always given numbers. If you do it in general form, you have more flexibility. And you can spot errors, because you will, for example, if your answer is, I don't know, R plus T, it's not possible because R is meters and T is seconds. You can't add meters and seconds. So somewhere you've made a mistake. And okay, so T is this, does not depend on alpha. And we can double check that. We can say, let's say it's falling along AE. Now it's in free fall. It's not sliding, it's falling along AE. Well, we have the distance, so we can use the suat here. Why not? S is equal to, well, 1/2 gt squared, because literally it's free fall, and initial position 0, initial velocity 0, and the distance is 2r. The distance to fall is 2r, is equal to 1/2 gt squared, and from here t is equal to 4r divided by g square root. So yes, it does not matter. If the ball was rolling, the acceleration would not be g cos alpha, because rolling takes away some of the energy. Some of the kinetic energy is going into rolling, is actually spinning the ball, and it depends on the shape of the ball. That's why most questions you say sliding down without friction rather than rolling down. Okay, so rolling down along any slope, even the shortest slope, even like a 1 micrometer slope, will take exactly the same time, which is quite cool. Finally, question 7. This has this looks horrible. A wheel radius r is rolling along a road. A small piece of dirt detaches from the wheel at A and lands at the exact same location on the wheel, of course. What is the speed? What is the speed v of the wheel? Well, we need to establish what type of motion, and of course it's projectile motion. It's projectile motion. So it's launched at some angle theta with speed v. Oh no, not speed v, of course. But not speed v. You need to find that. You'll need to find that speed. Let's call it u. And then it goes and it lands over here. It lands over here. Now, because this lands in the same location, the wheel has made one whole rotation. So it has traveled a distance of 2 pi r. The wheel has traveled one full rotation. But wait a minute, who said it makes one full rotation? Well, actually, nobody did. Nobody did. So we'll solve it for one rotation separately, and we'll solve it for n rotations. We'll solve it for n rotations, 2 pi r n. So let's do it for one. And well, the hardest thing is to figure out the initial velocity, because as long as you find out the initial velocity, then it's not a big deal. When a wheel is spinning, so at point A, the spinning of the wheel, like imagine the wheel was spinning on the spot, and point A would be moving vertically upwards. And now imagine the wheel was not spinning, but sliding. A would be sliding with the same speed as the wheel. So at point A, there are two components of the velocity. There's an upwards velocity, and there's a horizontal velocity. There's a horizontal velocity due to the movement of the wheel, so that is v. Now, point A is moving upwards, well, actually with the same speed. It's actually moving up with the same speed as the wheel is moving forward. So the initial velocity u is actually equal to square root of 2 v, using Pythagoras theorem. And this angle is 45 degrees. Why is it moving up with the same speed as it moving forwards? Well, you need to imagine that the wheel is spinning on the spot, and all points of the wheel are moving with the speed v. Like how would I show that? So imagine well, I don't know, imagine a wheel is spinning like this. All the points on the wheel are moving with the same speed. Cricket ball, if only I had one. All the points on the wheel are moving in, so they are moving with the same speed in different directions. But also it is moving sideways. So the wheel is moving sideways, but all the points are moving clockwise. So if you, at point A, you have the horizontal velocity is only due to the movement of the wheel, because if the wheel was spinning on its spot, point A would have only vertical velocity. We say it is a superposition of two movements, the spinning of the wheel and the movement. Is that, does that clarify things? Okay. Yeah, so you need to isolate the two movements, the spinning and the moving. And you will understand that the spinning and the moving happen at the same speed. Okay, now I'd like to think of a better way of showing that, but so you have these. You have the velocities, and then you just write the standard equations. Yeah, absolutely. So we write down x of t is equal to the initial velocity times cosine theta t. That's the horizontal movement, and the vertical movement is but we're not looking for the radius. We're looking for the speed. The speed of the wheel, of the rolling of the wheel. It's u sine theta t minus 1/2 gt squared. So equations that are already familiar to you, we need to assume that the origin of coordinates, the origin of the frame of reference is here. So this is the x-axis, and this is the y-axis. So the initial position and the final vertical position is 0. So this is the origin, and it's going like this. So from here, we have, this is the horizontal, this is the equation for the horizontal movement, and this is the equation for the vertical movement, u sine theta. So x of t, and we know that after t seconds, it hits the same spot. We know that at t equals t, after t seconds, x is equal to 2 pi r, and y is equal to 0. So effectively, we're solving can't we differentiate the radius vector? The radius vector. But that's what we're doing. This is the radius vector. Like, these are the components of the radius vector. And differentiate, I don't immediately see how it could be done. Probably yes, but let's we're running out of time, so I just want to finish this. So u sine theta t minus 1/2 gt squared, and as I mentioned, this is already t. Now we obviously know that t is not 0, So we are allowed to divide by t. We're allowed to divide by t because we know t is not 0. Because 0 is not going to be a solution to this question. So divide by t. So we have u sine theta minus 1/2 gt equals 0. So t is equal to 2u sine theta divided by g. 2u sine theta divided by g. This is actually a familiar expression. It is in the assignment. Now, if you plug that in to the first equation, so you plug that into the first equation, you get 2 pi r is equal to u cos theta times t times u 2u sine theta divided by g. And you get g, so 2 cancels out, and two cancels out, and we have g pi r equals u squared cos theta sine theta. Now remember that cos theta and theta is 45 degrees, so it's g pi r equals u squared square root of 2 on 2 square root of 2 on 2. So g pi r equals u squared multiplied by 1/2, because square root of 2 times square root of 2 times square root of 2 is 2, divided by 4 is 1/2. And then I found a mistake that I've made. Well, not here, but previously when I was doing this question. I forgot that u is square root of 2v. U is square root of 2v, so g pi r is equal to 2v squared times 1/2. So 2 cancels out, and we have v squared equals g pi r. So v is equal to square root of g pi r. This is the speed of the wheel. Now, but we have this expression after n rotations. But let's see if anything would be different for this one. And the only thing different is this. This is where the difference occurs. So let's plug that in. So it's going to be 2 pi rn after n rotations equals, so nothing will change until the very last moment. So actually the only difference, if you repeat the calculations, it's going to be square root of n g pi r. And I mean, what could the practical application be? Well, potentially it could be a circus trick, I don't know, with a wheel rolling and something jumping off. But basically, if you have to define, no, n is, well, n is an integer. And okay, n, we can say n is an integer here. N is 1, 2, 3, etc. For any value of n, you can find the speed that you need in order for the little piece of dirt to land at exactly the same point. Okay, well, that's it. U squared sine 2 theta. Yes, that is the expression, and it is in the assignment. So good luck with the assignment. It is due on the 5th of December. And enjoy. Welcome. Yes, we have. I will do webinars every week. Actually, yeah, I'll do webinars every week. So yes, see you. To tutors tonight. I have another meeting now, and hopefully, yes, I'll try my best. Sorry, I'm limited in resources, so I'll try my best to do that, to do tutors today. Could you still access the webinar? If you didn't get in, could you still access? Yes, you can access the webinar. The webinar will be published on YouTube. And what do you mean questions not working? Are you in the Telegram group, Arnav? Okay. Decision, yes. Decision, yes, definitely tomorrow. I'm very sorry. I'll let you know today if I manage to mark the remaining works, because somebody else was supposed to mark them, and unfortunately they disappeared. We lost them in Oxford. All right. Okay, see you. See you. Yes, to get in, you need 40% physics and 50% maths, or an average of more than 50% in both. Okay, see you everyone.